So, hi everyone, my name is Margot MAHIEUX. I'm currently doing my thesis between the ENGIE lab CRIGEN and the LBE of Narbonne. And today I'm going to talk about the stimulation of the organic matter biodegradability with pulsed H2 injection during in situ biomethanation. But first, what is H2 biomethanation? So briefly, when we are talking about H2 biomethanation, we mostly refer to the enrichment process of biogas produced during anaerobic digestion, so carbon dioxide and methane, with H2 injection. It follows the according equation. 4 mole of H2 are reacting with 1 mole of carbon dioxide to produce 1 mole of methane and 2 mole of water. So currently, when we are looking at the literature, the most advanced process is the ex situ biomethanation, where first we are doing the anaerobic digestion process in a digester, and then we are putting the biogas in a subunit where we are injecting H2 to produce more methane in that subunit. But today I want to talk about in situ biomethanation. So this is basically the same process, but all in the same digester directly. So when we are talking about in situ biomethanation, it could permit to reduce capital and operational expenditure economically for the industrial process, but we have also to consider that the H2 is impacting the full process of the anaerobic digestion from hydrolysis to methanogenesis. So in the literature, when we talk about in situ biomethanation and archaeal community, most of the researchers have been focused on the effect of hydrogen on either hydrogenotrophic methanogens that are consuming hydrogen to produce methane, and they are being in competition for that consumption of hydrogen during biomethanation, or either on acetoclastic methanogens that are being inhibited by the H2 injection during the process. However, about 90 to 95% of the anaerobic digestion community is composed by bacteria, and today there is no consumption in the literature about the effect of adding H2 directly in the media to do biomethanation. So my question for that experiment was quite simple. Does H2 inputs during in situ biomethanation affect the first step of the anaerobic digestion? Were hydrolysis and acidogenesis affected by SUS H2 injection, and were bacterial communities able to modulate the SUS activity within H2 inputs? So to answer this question, we designed the following experimental plane. I use a complex feedstocks to be close of the real anaerobic digestion, and 2 different inoculum, one from a main digester with a strong hydrolysis and acidogenesis activity, and one from a post-digester. And I put them either in anaerobic digestion condition, which was my control, or in situ biomethanation with pulse H2 induction, and I did a semi-continuous process. So with a 20-day HRT with a 1.5 organic loading rate in terms of VS, and I targeted a 4.1 H2CO2 ratio in the gas phase. And the feeding strategy was to feed the reactor either with H2 or feedstocks 3 times per week. So what were the results of that experiment? So when we look at the first week, which was the methane production of the first week, which was my acclimatation week, I didn't feed them with H2 at that moment, we can see that the digestate has a strong activity of methane production directly with the feedstock input, while the post-digestate has a weaker activity. Then we started to add H2, and so the methane productivity was really stable for the digestate either in anaerobic digestion or in situ condition, respectively in orange and red. But for the post-digester, we can see that the methane production was initially lowered, and then the post-digestate with H2 inputs, so in deep blue, was able to reach similar performance as the digester. So it gave us a first answer. Yes, the methane productivity, the activity of the post-digester was able to be improved while we injected H2. So H2 was not a problem for that improvement. Operationally, we obtained 80% of methane in the gas phase during the last part of the experiment, which was quite interesting. And we didn't have any VFA accumulation, which were due to H2 injection during that experiment. However, here, H2 represented only 40% of the introduced chemical oxygen demand. And you can see in here that the methane productivity has more than doubled. And when I did the mass balance, it was like we were obtaining much more methane than expected in situ condition. So I tried to look why I obtained much more methane. And so I look at the methane production in situ condition that could have been due to anaerobic digestion. So to do so, I removed from the total methane production the part of the methane that could have been produced with H2 injection. And so I compare them to my methane productivity to my control. And we can see that from week 0 to week 2, we had really similar performance between the control and in situ condition. And starting week 3, we started to obtain a higher anaerobic digestion activity in situ condition. So here we see increase of anaerobic digestion activity. The hypothesis was maybe H2 has a positive effect on the organic matter degradation. Maybe it was due to a stimulation of the archaeal population. And I also have to make you notice in here that we were having a higher pH due to H2 injection in situ condition. So we looked at the organic matter degradation through fractionations that permitted to see the organic matter in fraction from the most to the less accessible, and also the degradation of the organic matter across time. And with that fractionation, we obtain the following results. So here you have the fraction from the most accessible on the top of the graph to the less accessible, considering the initial substrate and then the whole assessed condition at the end of the experiment. And what is interesting here is the purple part, which is the part of the organic matter that has been degraded during the experiment. And we can see that 20% of the organic matter has been degraded during that experiment, which confirms what we see. Yes, we had a better organic matter degradation that permitted to produce more methane thanks to anaerobic digestion. And so, as I was saying before, we look also at the microbial community to see what could have happened to that microbial community. And more specifically, here I want to talk about archaea. So here you have the microbial community at the beginning of H2 injection, which was more or less well balanced with a lot of different archaeal genus. And then at the end of the experiment, we see that we have one dominant genus in situ condition, which is in light blue. And so this genus is Methanocorpusculum, which is a well-known hydrogenotrophic methanogens. And so that hydrogenotrophic methanogens was able to consume H2 and so grew a lot in situ condition. And so when we are comparing the archaeal over bacterial ratio, which permit to see the improvement of the density of archaea in the population, we can see that we obtain about like 10% of archaeal over bacteria ratio in situ condition, while the ratio stays stable in AD control. So that permits to see that we really increased a lot the amount of archaea in the population. So to conclude, we saw that operationally we were able to obtain similar performance in the digestate of digester and post-digester, which could be good for industrial perspective because it would reduce the economical risk for the implementation of such a technology. We also obtained 80% of methane in the gas phase at small scale in only 3 weeks, which is a good prediction before trying to do bioreactor, for instance, for me. And H2 permitted to obtain a better organic matter biodegradation, so which is an interesting point to study to see in an optimization point of view how we could use that information to perform better in situ biomethanation process. As scientific conclusion, we saw an high enrichment of the hydrogenotrophic archaea population, and it led to a drop in the diversity of archaea. So what could be the impact of that loss of diversity while facing an environmental stress in the process? And we also saw that H2 had an impact on bacterial population, so which part of SUS variation was due to H2, to pH, or to impact on other abiotic parameters. Thanks for your attention, and thanks to my colleague.